Okay, so let's start. And after 14 minutes, I will stop the presentation. I think your presentation is supposed to be 8 to 15 minutes.
Okay.
So yeah. Okay, so let's start.
Okay, so I did my presentation on the variables that affect the development of obesity.
Mhm.
The objective of this, so first there's a rising problem, especially in the US. And so it can easily be prevented with any knowledge on the factors that contribute to one developing obesity. So my goal of this presentation or of this project was to determine the factors that most contribute to one developing obesity, as well as determining a model that best represents that data. So what does the data describe? So my data set basically assigned categories to people based on a whole bunch of factors, mainly their BMI, which contributes their height and weight. And it also takes into account like eating habits, physical condition, family history, environment, things like that. Time using technology. It had 17 different variables and it had 2,111 samples. And so of those samples, 23% of those results were self-reported. So maybe through surveys or someone filling out answering questions and everything, so surveys. And then 77% of the results were also generated synthetically using a Weka tool and a smoke filter. So basically it takes just a bunch of data from the population and says like, hey, this is data from maybe past studies or other surveys not pertaining to this, and this is what we have developed. So components of the data set, I did have to remove some variables that were repetitive or irrelevant to my overall goal. And so with that, I removed things such as frequent consumption of vegetables, number of meals, as well as age. And I just removed especially age because my project basically solely looked at the BMI, and I felt as if the age would not really help. And then other factors such as like frequency of consumption of vegetables or like frequency of consumption of water, it just kind of fell into another category of the data set, which is, number of meals that you eat or how often do you eat between main meals. And so the dependent variable of my data set was the obesity level. And this is an ordered categorical model. And so this did pose as an issue because we did not learn how to do this. And so what an ordered categorical model does is it assigns groups based on certain factors. So in my case, insufficient weight would be the lowest group and obesity type 3 would be the highest group. And from there is based on BMI, and you are categorized based on different results. And then some independent variables such as consumption of food between meals and consumption of alcohol. Those were also ordered categorical models, but that one was based more on, rather than weight and height, it was based on frequency in which you're doing something. So how often do you eat or how often do you drink alcohol? So for my methodology, first I regressed obesity level onto my lifestyle variables using the POLAR. So basically this is using regression, but it's specifically for ordered factors. So for that ordinal categorical models. And so then from there, I evaluated the p-values. And then I tested which regression model fit the data the best. And so I used 3 different models to compare it against, which is the probit, logistic, and log-log model. And you'll see later on in the presentation which one fit the best. And then I used backward deletion iteratively to drop the unnecessary predictors. So that's us looking at the AIC. And then I used ANOVA to conduct a likelihood ratio test of these models. So if I were to delete this from a model, if I were to use this specific model, how well does those compare to one another? So are they significantly different? And then I created a pairs plot of the profile cases, and that did create two curves which intersect at maximum likelihood estimates. It does look different than most pairs plots that we have created in class. Then I manually calculated my BMI using, I think it was weight over height squared. So I had to convert everything to SI units and then do that. And then I made two contingency tables. One just using a linear model between BMI and family history, and one using the KNN, or the K nearest neighborhood test, using K as 10 to predict development of obesity based on familial history. So I just limited to BMI and family history for the last two, just because they were easier to encompass and they had less categorical things going on. So for my first set of results, I just used, I don't know if you can see the polar, and this is for the ordinal variables. And from there, I found the p-values. And from these p-values, we can see, or it's not shown here, but I also calculate the p-values. And smoke had a larger p-value than 0.5, or alpha of 0.5, 95% confidence. And it had a p-value of 0.21. And the consumption of alcohol had a p-value of 0.91, 0.54, and 0.35. So there are three different p-values for the consumption of alcohol, because the POLAR test does look at how the models result if you use a linear model, quadratic model, or cubic model. So those three p-values are for the linear, quadratic, and cubic, and none of them fit the data set. All right, and then from there, I use logistic regression to produce the lowest AIC for the data, which created the best model. And so I got this result because when I did create the different models, and I specified whether I wanted to use probit, log-log, or logistic regression. The logistic regression was the only one that decreased the AIC, which means it's a better fit. And the other two did increase it, which means it's not as well of a fit. And then using the backward deletion, smoke was eliminated, and which is consistent with the p-value that was calculated from before. And then the AIC decreased from 7119 to about 7118. So it did get slightly better. All right, and then when comparing my alpha value, the p-value is greater, which means that we can accept the null hypothesis. So what I did was I did a likelihood ratio test for the ordinal regression, and which is comparing the two models of smoke included compared to smoke not included in my model. And because my p-value was greater, you do have to accept the null hypothesis, which means that the two models do not significantly differ overall. So there was no major difference if smoke were included with the data. So if the person smokes, that did not make a huge difference. Okay, so this was the pairs graph that I was talking about earlier. It's not as pretty just because there are many different variables, but a little bit description about how this pairs test works is that it takes the X and Y parameters. So in this case, the obesity level would be the Y parameter, and the X factor would be maybe gender, family, FABC, so on. So the FABC is just like the consumption of high calorie foods, okay? And so from there, I converted, if anything were a yes or no question, I converted it to a numerical value of 1 for yes or 0 for no. And then I regressed it onto the two lines. And we can see as they intersect with one another, that is the maximum likelihood for those two to be correlated to one another. So we see gender and the obesity factor right here. I don't know if you can see my mouse, but and then we compare it to these two numbers, and those are the two likelihoods of the two. All right. And then finally, I made two different contingency tables. The first contingency table, I wanted to predict the obesity based on familial history. So once again, I created, I converted if it's a yes, no question. So does the person have history of obesity in the family? Yes, that would be 1. If no, then that would be 0. So first I converted those into a binary response. And then I compared that to the presence of obesity. So instead of using the obesity levels from before, so the categorical levels, I created my own and first calculate the BMI manually, so doing weight divided by height squared. And then after that, I researched what's the what's the healthiest BMI you can have, the top BMI you can have for it to be considered healthy, and anything over that, I classified that as obese. So in this case, it'll be 24.9, and below was classified as normal weight or healthy, and then anything above that was classified as obese. And then from there, I compared the two. So if you have family history, are you going to be considered obese? And so based on that prediction model, it created a model that had 18.3% error. And then finally, I wanted to see, can I test my model in a different way? So I created the K nearest neighbor test. I conducted that. And again, I used the BMI compared to familial history. And what this does is it randomly divided the data set into a training set and test set. So I had it divide, if it had 2,111 response variables, I did 1055 and 1056 as a training set. And then I randomly selected those. And then I created my KNN test. And so basically what the KNN does is it takes the 10 nearest points or 10 nearest values and finds the mean and sees, is this an accurate prediction? And based on this, it was not an accurate prediction because it did have an error rate of about 45%, which is relatively high. All right, and then for my final slide, I just discussed some future improvements of my data set. So my first thing I could probably do was include more variables when analyzing BMI and obesity. It was a little difficult to include other variables without any confounding factors because I had to pick and choose, hey, is this a repetitive variable or are these directly correlated? So we know that height and weight are going to be correlated to one another. And after a while, because it's based on BMI, that's why I was able to calculate BMI. Whereas if I directly only correlated height and weight, it wouldn't have been an accurate representation. So I had to take both into account and then compare that to other results. So I would have had to do that with other variables as well. And then age, I feel like that could have been a little bit of an insight into, as you age, is your BMI going up? Is it going down? Are you going to be more obese when you're older, less obese? Does it have anything to do with physical activity? And then my other improvement I think I could have done was plot more correlation models. The main reason why I did have difficulty with that was because there were too many binary response variables, so too many yes or no variables. And because there are so many yes or no variables, it's very difficult to graph a graph. I tried to graph it, it was just 4 dots on a graph. So it is difficult to show an accurate representation of that unless it's going to be some type of correlation graph. And then correlation plots can mostly only be created like I did, like the pairs plot. It's very difficult to do just like a regular plot of my data or do a scatter plot with the AB line. It's very difficult because everything is a yes or no, so binary, like 0 or 1. So yeah, I think that is it.
Thank you, Zoe. Yeah, I think it's interesting topic. So does anyone have questions to Zoe?
Zoe, where did you get the data?
I got the data from, it was wherever we got the data set from the homework. Let me see. Well, there was an article written in a scientific article called Data Set for Estimation of Obesity Levels, and that was published in Science Direct. And that did give you access to the direct data, but I got it from another data site that gave a whole bunch of data sets. So I just referred to the paper to look up, what the different abbreviations meant, how do they correlate, how did they find the data?
Okay, thank you.
Yeah, good. Other questions? If not, I have some clarifying questions. So in the first slide, you did the ordinal logistic regression, right? Then
Yes.
after that, you do some binary models. So what's the threshold for binary model? The obesity and overweight, the between those two is the threshold to make response variable binary?
No, so the binary was some of the questions that was asked in the data set was, do you have a family history of obesity? Yes or no? Or do you eat 3 meals? Yes or no? It was just yes or no responses. And then
I mean response variable. So the
and then a response variable, the categorical data, it went in order of, so I was looking it up and it went in order of BMI. So if you were below a certain BMI, like 18 or something, you're considered insufficient weight. And then from there, every increase in BMI had a specific categorization until after you're over a certain point, you're just compared to obesity type 3.
Yeah. So, but in logistic or probit models, it sounds that you did binary prediction. Is that right? The first slide is the categorical, I mean the ordered categorical regression, but the logistic probit KNN, it sounds that your contingency table is 2 by 2. So I think it's binary prediction. Is that right?
So my contingency table, I didn't do it on the obesity levels. I created, that one was binary response.
So what's the threshold? The obesity and overweight is the threshold, or
it was like normal and
normal
then
and
overweight.
Okay,
yeah.
I see.
So I made a note of that in my code, but basically I just calculated the like the normal BMI for everyone based on height and weight, and then from there I made that a binary response.
And sorry, I have some technical questions. So the correlation plot is interesting. So which package did you use?
So I actually had to look this one up because it was very difficult to plot a normal pairs plot with
I understand, but which package did you use? I have seen this for the first time. So
I had to download, let me see, I'm pulling it up right now. I downloaded it was like NNet.
Okay, I see. Oh, NNet. Okay, I see.
Yes.
Yeah, that makes sense. Yeah. Okay, thank you. And sorry, what's these variables, the FAVC and SCC? What these mean?
So FCC, so FAF. I attached the when I did turn in the code or the data set, I did attach the paper just in case you wanted to look up like like what the meanings meant. But like TUE is like the time on using like a technology device. NCP is like the number of main meals. FAVC is like the frequency consumption of high caloric foods.
Okay. Oh, okay, I see.
Yeah, so it was very difficult to include all 17 of those variables.
Yeah, sure. Yeah. Okay. Sorry, the last question. So in slide 11, I think the prediction of obesity based on family history, the first contingency table. So this is for the training error. I mean, you showed 2 contingency table, and the second one is obviously the test error size. And the first one is for the training error size, or?
No, the first one, I compared, so I like created just a simple linear model based on the two. So based on the two response, the response variable and the predictor. And then from there, I looked to see, is this actually true? So after like, is my linear model true based on the actual calculated BMI? So that's why I had to like calculate the BMI separately and put in manually, like if it's greater than this, it's going to be overweight, or if it's less than this, is going to be normal or insufficient.
Thank you. Okay, thank you for your presentation. Yeah. Yeah, I think a couple of days ago, I see some graphs that which shows the skyrocketing the obesity in the United States, especially after 1980. So I will teach time series course next semester. So if anyone is interested in maybe time series analysis of obesity rate is also interesting. Okay, so it's great. And next, Ryan, sorry. I'm not sure how to, yeah. Yeah, you can start.
I can see you talking, but you're muted, just so you know.
Okay, there we go.
You're fine.
All right. Yeah. Brain fog from having a migraine for 2 days. I'm going to do my best. So you guys can see my slides, right?
Yes.
Okay. So I decided to do my final project on the Ames housing data. And my goal was to predict the neighborhood based on some of the factors. So this is just kind of the structure of my presentation for today. I'm going to go through the introduction and background, the data understanding, the data preparation, the methodologies that were used, and then the results and conclusion. So for project understanding, the background of my project is, imagine that you're a buyer and you're moving to the city of Ames, Iowa, and you have a list of criteria that you want met in the house that you're going to buy. And so you just want to know, like, what neighborhoods should I be looking in order to find a house that has all of those, that meets all those criteria. I am trying to predict what neighborhood a house is most likely to reside in based on the house features. So I want to design a classification model that will predict neighborhoods based on a selection of house features or explanatory variables that hold the most significance in determining the neighborhood category. So I got my data set. I originally got the data set from Kaggle, but I later ended up finding the same data set that was pre-cleaned to a certain extent from the Tidy Models package, and that's what I ended up using for the majority of my analysis. This data set contains information about residential properties sold in Ames, Iowa from the year 2006 to the year 2010. The original data set contained 2,930 observations, had 82 columns, 23 of them were nominal, another 23 were ordinal, 14 of them were discrete, and 20 were continuous. 2 of those variables ended up just being identifiers, and so those were removed later on. I have a full PDF that explains all of the variables and what they mean. Some of them included the style of the house, so if it was a 1-story or a townhouse, those kinds of identification. Some of the variables just described the condition of various aspects of the house. And other information included the year built, the year that it was sold, etc., and of course the price. Data understanding. So first we have to collect and describe the data. We did exploratory data analysis and then assess the data quality. I decided to start out with a couple of charts with the distribution of the houses sold by neighborhood. And this was showing us that there were some neighborhoods that had significantly less sales than other neighborhoods. And because of the type of analysis that we were going to be doing, we ended up just removing those categories completely. I also created a correlation matrix. This shows the strength and direction of the linear relationship between the given variables. And you can see that the variables that describe the square footage of various aspects, so the basement, the first floor, and the second floor, those are all pretty moderate to highly correlated, which makes sense because your first floor is going to be about the same size as your basement. I also created a box plot to look for any outliers. There were a lot of outliers, and part of this is due to variables that were not common across all of the observations. So there were relatively very few observations that included a pool. And so variables like pool square footage are going to have a lot of outliers, because basically anything that isn't a 0 is an outlier in that case. So there was a lot of data preparation that had to be done for this data set because there were so many variables. And as we saw, a lot of them had a lot of outliers. So all of that had to be taken care of before we were able to actually run the analysis. I chose to use multinomial logistic regression, and you can see the formula that is used for that model. And that's where P is the probability of the dependent variable Y being in category K, given the value of the independent variable X. This is good for relationships. Sorry. Between a categorical dependent variable with more than 2 categories and 1 or more independent variables. Categorical outcomes that have no natural order, which is what we had, because there's no order across the neighborhoods. They're all rated the same. And it also accounts for the fact that the outcome is not a simple binary variable. So the multinomial logistic regression has a few assumptions that have to be met in order for it to be used. The first being independence of observations. This means that the data should not have any hierarchical structure and no dependencies between observations. It should also have an absence of collinearity. So the independent variables should not be highly correlated with each other. This can make it difficult to estimate the individual effects of each variable on the dependent variable. It should also have a large sample size, which our data set definitely did. Multinomial logistic regression usually requires a large sample size for the estimation of coefficients to be reliable. That means that there should be at least 10 to 20 observations per independent variable, which is why we had to remove some of those neighborhoods as a whole, because they only had like 1 or 2 houses sold. We also used lasso penalty. The equation for that is on the slide as well. This is a regularization technique used to prevent overfitting and improve the model's generalization performance by pushing regression coefficients toward 0 and effectively performing variable selection. This was important because we had so many different variables that it would have been impossible, or at least taken forever, to run a model without selecting a set of those variables. Lasso penalty is also useful where multicollinearity is present. So the results of the multinomial logistic regression with lasso penalty was only an accuracy of 51.71%. This wouldn't normally be considered very high, but within the scope of this project, it was kind of the best that we could get. Multinomial logistic regression with lasso penalty was used to classify which neighborhood a house would be in based on a variety of factors. The model performed with approximately 51% accuracy. For future analysis and future studies, I think that it would be a good idea to compare this model with alternative models. It would also be useful to perform a cross-fold validation and also just conducting research on what features are considered to be most important by the majority of, that's a typo there, it should be buyers, not sellers, but what features are most important to the majority of buyers, just because it would give a better starting point to be able to pare down the number of variables that we're looking at for the analysis. And then you would retrain the model with only that set of variables. And I think that that would be a really great next step for this project. And that's the end of my presentation. Does anyone have any questions?
I had a question. How many neighborhoods were there for the model to choose from?
Yeah, that's a great question. I should have put that in here. I believe there were 28 or 27 total neighborhoods. I think it started with 28, but one of them had 0, so it was immediately taken off.
All right, thank you.
Yeah. Anyone else?
Yeah, actually, the Erica's question is the question I also thought about it. And if there are 27 or 28 categories, probably 51% is pretty good number.
Yeah, that's what I was thinking too.
Yeah.
With as many variables that there were and as many categories of neighborhood, because each neighborhood was its own category. 51% did seem pretty strong, but it can always be stronger.
Is 51% training error or test error?
It was the accuracy score for, I believe it was the test model.
So I forgot the sample size, but how much of the observations are used for test?
I had a 70-30 split.
Okay. Reasonable. Okay. Yeah, that sounds interesting. Yeah. I think originally probably this Kaggle dataset is, usually for housing price prediction. But
yeah,
it's interesting to predict.
I was trying to make sure that I was picking an objective that was significantly different from what the actual Kaggle competition was based on. So I was trying to use price as little as possible. Although price, one of the findings was that in other research, that price was highly correlated with neighborhood, and each neighborhood had kind of its own pricing structure, which was interesting.
Yeah, it makes sense here. Okay, great. So thank you. And just make sure that you can upload the files and also the R code to the
yes,
absolutely. In Canvas later. Okay, so the next one is, I think, Nathan.
Okay, give me 1 sec.
Sure.
Oh, I got it. Okay. Here we go. Let's make it big. All right, can everyone hear me?
Yes.
Okay.
No problem.
All right. Perfect. Okay, so my project is on the lithology of soil samples, and I will explain what that is in a second. But basically, the idea is to predict what soil looks like based on what it is. So let's get started. So like I said, lithology is for a geologist, it's when you have soil sample, meaning like the rock part, not the organic matter part. When you do it, or when you look at it, you can tell whether or not, if it's sand, if it's gravel, if it's clay, etc. And then also there's some other variables, which I've actually accounted for, which I'll get into in a second. So the idea, oh, I need to hide this. Okay, the idea is, can we use statistical learning to see if the soil sample's appearances match their actual composition? Like if we took it down, or if we separated into its categories and weighed them and found the percentage each one weighs, could we be able to tell what it is? In addition, can we use other predictors to do that? So there are two sort of objectives, and one is how well can we predict what its soil will look like with new predictions? And what I mean by this is, say a geologist would uncover some soil. Can we predict what how the geologist would view it based on what it becomes? And the other one is it safe to use the appearance to determine actual soil competition? And this question actually is not directly answered, but we will talk about how we can answer that at the end of the presentation. Okay, so let's talk about the data. So the data is from data.gov. It's a superficial sediment from the US Geological Survey. And there was 28,000 soil samples. Unfortunately, as you can see, about 99% of them were not actually useful. They were missing important data. So what was actually there were 13 predictors in total. So the latitude and the longitude of where the sample was collected. The samples were actually for all around the world, but the ones that actually made it into this 308 useful ones were all from the US, Canada, or Mexico. We have the depth, which is because they were along like coasts or rivers, how far underwater each sample was. And then we have percentage by weight of gravel, sand, silt, and clay, which is just it's like more broad category of weights. And then there was these phi's down here, which is percentage of each weight, but they're finer categories. So it's like where you actually measure the size of the particulate. There were actually several more phi layers that just kept getting finer and finer, but ultimately there was a lot of missing data from those, and I imagine it's hard to judge accurately anyway. So let's talk about what we did. So we made an indicator variable called sand, and since oh, that's a typo, but the lithology was provided as strings of all caps for us. So we found the lithology that has the word sand, but not the word silt. And the reason why is to avoid this particular lithology, which appears frequently. And I used regular expressions to do this, although I'm not the greatest computer scientist, so I couldn't get any finer. We were therefore stuck with binary data, which actually works to our advantage for this particular case. And then finally, just so I would have some sort of comparison, I generated this 61 element universal training set for direct comparison, which is basically a fancy way of saying I bootstrapped a sample that was 1/5 the size of the data, and then I produced contingency tables for each of the models I used so that you all can see them, just for comparison, for a example comparison. Okay, so let's talk about the data. These were four numerical predictors that ended up being important to my research. So you can see that obviously the percentage of the sand ended up being pretty big difference between this column is soil samples with sand and the word sand in the lithography, and this one is without. So you can see obviously we'd expect more sand than the one that said sand in the lithography, or lithology. Although there's still a substantial amount of sand in the other ones too. Clay is kind of weird because of the way R does these box plots, but you can see that this is less than this one. And then these were the two largest predictors, which I found interesting because these ones look about the same, but this one was pretty big. But the biggest thing that surprised me, the thing that kind of makes obvious sense in retrospect, was when I averaged the latitude and longitude of the two groups, and I plotted them on the map. And you can see right here, it's pretty interesting. The ones with more sand is along the beaches, which I guess you wouldn't think about, but it does make sense. And actually the average latitude and longitude of the ones without sand is pretty close to where we are, I guess. And so I just plotted these two plots on the globe, and yeah, it's kind of interesting. There's a lot of insight here that I think can be sort of displayed pretty nicely in this graph. Okay, so the idea, we're going to use logistic regressions and LDA, and we'll compare it with the tree, the classification tree, to see whether or not a linear decision boundary is appropriate. And then if we decide so, then we'll fine tune the boundary using SVM with different kernels. So that's what we did. So let's talk about logistic regression. So I had two formulas that I used. This is just sand regressed on all 13 of the predictors I had earlier. And I was worried about overfitting. So what I did was I ran backward deletion AISC stepwise formula, and then this is the formula that ended up being useful. And something interesting is actually when I went for the smaller formula, you can see the tenfold cross-validation error is actually smaller with the smaller formula than it is with the bigger formula. So it looks like my fears of overfittings actually were somewhat accurate. So this is the better contingency table on the sample observations I ran. You can see it's pretty good actually. And then I did one final test, and this is probably not surprising, but I did a test by deviance, which I don't remember if we covered in this class, but basically, if you have it basically allows you to see if a bigger model is significantly better than a smaller model. And at a significance value of 0.05, we're nowhere close to it. So complex is not really the option here. But yeah, you can see it did pretty good. A simple logistic regression was pretty successful for this. And this is binary data, so it's probably not super surprising. Let's talk about LDA. There wasn't really a good way to do cross-validation using the libraries for my class. So I bootstrapped 5 times, and we can see the error rate was a little higher for LDA, which is kind of I guess not really surprising, because that tends to just be like my experience with LDA is it's just a little better than that. So you can see, here's another example. You can see this is actually the same correctness, but we got these two categories mixed up. So you can see we have a 26% cross-validated error rate, which is not particularly great. So now we'll talk about classification tree. So I used cross-validation tree. I did tenfold cross-validation. We got a bigger tree for Formula 1 and a smaller tree for Formula 2. Now, what I find interesting about it is that the tree was the only structure we'll talk about today where the bigger formula was better. So yeah, we got a lower error rate. And actually, interestingly enough, even though the cross-validated error rate was smaller, or higher, I'm sorry, this cross-validated error rate was higher, but our bootstrap sample, it actually performed slightly better than the other two, which I found interesting. So they're pretty close. But I feel like the computational overhead of tree just does not make it worth it in the long run. So since it looks like the linear decision boundary, which I had predicted was going to be better, so I wanted to run SVM with a bunch of different kernels. So I put them all here. Unfortunately, my computer was not powerful enough to cross-validate these gammas for the cubic polynomial. But even so, you can see that the linear formula with the smaller one was a little better. And I put the contingency table up here because this one's crowded. And it performed about as well as the first two, which is what you'd expect, I guess. But you can see I have linear formulas. This is the full formula. This is our restricted formula, and so forth for the cubic polynomial and then radial. And you can see even with like the sort of double cross validation, the linear formula is still better. So what can we conclude from this? And it seems like linear decision boundaries do seem appropriate for this project, which doesn't surprise me. I guess there's probably also a high degree of correlation between the variables, so it would make sense. Logistic regression overall was pretty good. Considering it's considerably easier on the computer versus SVM, I'll just go back to it real quick. So you can see it gets pretty close actually. And that's all right. I think all things considered, support vector machine is going to be the best result. but overall, I'd say, yeah, logistic regression was perfectly fine. And I guess the moral of the story is the geologists know what they're doing. Geologists can seem to pretty accurately determine the composition of soil by looks. So I guess there's no issue on that. So the next question is where to go from here. And like the immediate next step would probably be to do some sort of unsupervised learning. And the reason for that is because it allows us to handle more than one case. And then we could also see it once we cluster it out or something like that, then we could compare the lithologies. We could compare the lithologies. And then we can just manually look and see if they actually make sense. And who knows, maybe silty sand and sandy silt are closer than one would initially think, which is pretty cool. And then I had an idea for going the other direction, even though it's a significantly more complicated, trying to predict the soil composition using images. It might be possible to do it using deep learning, although I'm not really familiar with image classification. And also, I was just given string descriptions of the data and not the actual pictures. So I wasn't the one making the lithology, but it should be possible in theory, at least to some degree. And overall, I'd say we did pretty well actually. 20 less than 1/4 error rate seems to be pretty reasonable in my opinion. So and then that's kind of it. These are the links. This is the cool plotter I used to make that map, which I found really insightful. And other than that, I just have the data, and everything else was from the lab pages in the book. So I guess that's it.
Okay, thank you. Yeah, it's interesting presentation, and yeah, methods and analysis are clear. Do you have any questions?
I just don't quite, I like what you had. I love the fact that you ran a lot of different models. Oh shoot, should at least bring myself back up. When you're talking visuals versus composition, I didn't quite, I may have missed it, but I couldn't quite figure out where the visual part was coming from. Is that just is that a call out in the test, or where was it?
So when my understanding of this is probably a very simplified model, but basically the geologist, when deciding on the lithology, will physically examine the sample and write a English language description of it. What I did was I used regular expressions, which is like a computer science construct.
I'm very familiar with them. Yes, thank you.
Yeah. Okay. What I did was I used regular expressions to classify the lithologies into broader categories.
Okay, so the same data set had a visual and a geologist input and then an analysis input between the two in the same sample.
Yes, but we only got we didn't get access to. I didn't see the soil samples. I just saw what the geologist said about them, if that makes sense. So I got the lithology. I didn't make the lithology, or I didn't have images to put with each of the lithologies.
Oh, okay. But no,
so I just had the English language string of characters.
That's still valid. That's still valid. Then you had an analysis of the individual, or each of the soil samples that were there actually had a materials analysis or a materials breakdown.
Correct.
Okay.
So yeah, so we just
you got this stuff.
I was making sure effectively that the materials analysis alongside the location of the sample aligned with what the geologists were saying about said samples, if that makes sense.
Now I got it. Thank you very much.
Any other questions?
Yeah, I had a quick question. So I know you said that you basically deleted anything that was that said 2 words like sand. It either had to say sand or silt. It can't be like sandy silt. Would it be possible to make like an intermediate like type of category for that, because I'm sure you had to delete a lot of data because of that?
So I actually had originally planned to do like something like a multinomial logistic regression. It just ultimately I could do I could do different models than what I initially planned if I stuck to binary data. I really wanted to do support vector machine. So yeah, you could absolutely do you could have ones that say sand and not silt, and then you could have ones that say both, and then you could have ones that just say silt or something like that. And then you could have like a odds and ends type of category. That's totally possible. I just wanted to run more models. So I kept it to binary for that reason.
Okay.
Makes sense. Okay, so maybe for the last presentation, so can Victoria share the screen?
Yeah. Okay. Hello, everyone. For my final project, I use the dataset named in vehicle coupon recommendation. I can see the words over here. Sorry. Introduction data. Sorry, let me move a little bit because it covers my work. Okay. This data study whether the person will accept the coupon recommended to him in different driving scenario. This data were collected via a survey on Amazon technical show. The survey described different driving scenario, including the destination, current time, where the passenger enter, and then ask the person whether he will accept the coupon if he is the driver. And this dataset I have in this website. Data distribution. This data has 12,684 observations. After remove row containing missing value, which generate 12,079 observations. Consider different variable demographics variable like age, gender, and context to attitude variable like weather, destination, etc. In total, 22 variable with 21 predictor variable and 1 response variable Y. With number 1 accept coupon and 0 reject the coupon. And here the correlation plot with all the variable, 22 variables, and you see over here the high correlation between the time and the temperature, high correlation. And this one, the chart for correlation plots, and in here, this one, the scatter plot with the trend line, with the, like you see over here, 0.21 for the correlation between the bar and the age. When you see the star like this, that means a significant correlation. With the star, no significant correlation between two variables. Like over here, 0.31, that means significant correlation, or negative 0.45, that's significant correlation. Methodology, I use three different I use three different method to do for my analysis. The first one, multiple logistic regression, and the second one, linear discriminant analysis, and the third one, the boosting. And I do the same thing for all of them with area under the curve for all of them, and after that I do the correct rate for all of them, and I compare them together. Which one has higher? You see that means area under the curve or higher correct rate. I would pick that for my prediction. This one, area under the curve, for the full model. And you see over here that respond with number 1 accept coupon, I'm sorry, and 0 for reject the coupon and all my variable in my model. And you see over here, I do the AUC area under the curve for multiple logistic regression with AUC 0.747. And the same thing for linear discriminant analysis, AUC 0.747. But with the boosting, I had the high AUC 0.987. And this one, I do the same thing, AUC by 5-fold cross validation for all of them. And with the multiple logistic regression, the AUC get a little bit higher, 0.758. And the linear discriminant analysis, the AUC get a little bit lower, 0.29. Putting a little bit lower, 0.852, but still higher than multiple logistic regression and linear discriminant analysis. Correct rate. This one I use the contingency table to do the correct rate. And this one, I picked the full model for all of them. With multiple logistic regression, I had correct rate 69%. For linear discriminant analysis, the same correct rate. But the boosting, I had a high correct rate for 94%. And this one, I run the same thing, correct rate for all of them, but with 5-fold cross validation. With the multiple logistic regression, 80% get higher than before, and the same thing for linear discriminant analysis, the same correct rate. With the boosting, it's a little bit lower, but still higher than multiple and linear. And this one, I divide the data sets into a test set and training set, and I randomly and replacement with 5-fold cross validation. And I had correct rate for multiple logistic regression and linear discriminant analysis, the same correct rate 69. The boosting get a little bit lower, 77%. And that means with the AUC and the correct rate higher than other two models, that's why the best model I pick for my prediction, that the boosting models. And with the boosting model, and I see the variable important for prediction, that the most important variable is occupation, and after that, the coupon, time, education. That's right, that over here. Less important. Up, that means more important. Available for my response and for reason. Okay. I find some summary very interesting. That means the best model for my analysis is boosting, and some other point I find very interesting for my finding. The probability of accepting coupon of the male are more than the female. The probability of accepting coupon of the single are more than other status. That means the married or unmarried partner. And the probability of accepting coupon of education, some high school are more than other education like associate degree or some like bachelor degree. And the coupon offering around 6 p.m. is accepted more than other time. I believe because 6 p.m. The people get out the job or the dinner time, so that's why easy to accept the coupon this time offer this time. And any kind of coupon like restaurant rather than $20, coffee house or carry out takeaway, or bar restaurant from $20 to $50 coupon are accepted. Thank you, everyone.
Yes, thank you, Victoria. So does anyone have questions?
I liked it. I'm not saying I have major questions. She covered most of most of what I saw. Nice job.
Thank
Yeah,
you.
it's a very nice job. Yeah, it's very clear comparison. Also, that she uses the AUC, and also it's interesting that the Nathan and the Victoria has a kind of similar statistical objectives. So compare the linear ones and the nonlinear ones, and the actually the conclusions are opposite, right? So Nathan's the data linear model is sufficient, actually even better. And Victoria's model, the more nonlinear model, is better. And of course, data are different, so conclusions are different. But also the sample size, this data has about the 12,000 observations. So we can see slight difference from linear model and a little more complicated model. So yeah, that makes more sense. I have one question. So in slide 9, you have 2 cross validations. What's the difference between those two? The second line and the third line. What's the difference? The full model with 5-fold cross validation and the test set and the training set with 5-fold cross validation. So what's the difference between these?
Which line? Which number one, Professor? Which one?
This slide, yes.
This slide. Okay.
Yeah.
Can you ask again, please?
What's the difference between second line and the third line?
Second here and the third one.
Yeah.
This one, I picked the full model, but I don't divide the data sets into the test sets and the training set. This one, I run the full model for with 5-fold cross validation. With the third one, I divide the test set and the training set, but and also randomly and replacement, and also I run with 5-fold cross validation for the third one.
So I'm still not sure. The second line is usual cross validation.
Yeah.
And this third line, you use the training test approach combined with cross validation.
Yeah, right. I do that.
So does that for hyperparameter tuning? So you tune the parameter with
and then I pick them with the for the for loop, and I compare them, the test set and the training set, and but I still put in the, and after that I add them together and then divide for 5, because I think that for 5-fold cross validation. When I had the correct rate and I add them together and then divide for 5. It's not correct. That means I divide test set and training set, and with replacements and randomly. And I use the for group for 5 times, and I had the correct rate for 5 times, and after that I add them 5 times together, 5 correct rate together, and I divide for 5, and I got the mean for the correct rate.
Okay. Sorry, I'm not still exactly sure. So the third line is not really for hyperparameter tuning.
Yeah, no.
I'm not sure. Yeah, maybe I will check the code. Thank you.
Yeah.
Okay, so thank you for all presentations, and again just the write comments on each of the presentation. So the comment form is available in Canvas, and each comment counts as one quiz. Okay, and also I will ask you to vote for the best three presentations at the end of the semester. So just to keep track of which presentations are the best.
I have a question.
Yeah, sure.
Do you want us to comment on our own? Like, we just say, like, I did this?
Sorry.
Because you assigned our own presentation to us too. So do you want us to just write a random comment for our own?
Oh, sorry. Yeah, so for your presentation, just write down like that this is my presentation, something to get 1 point. Yes, that's fine. Okay, so next time I think the Tauhid and the James and the Erica and Hunter. I'm not sure that Hunter is still in class, but we will have the 3 or 4 presentations. And yeah, do you have any questions? Yeah,
No,
I will also no, okay, so I will also upload these presentations, I mean the video today. Okay.
This is due in 3 days. The commentary is due in 3 days, right?
Comments are due in 3 days, but for the last day's presentation, comments are due on the next day at noon. So only you have about 17 hours.
I'll have them done today.
Yeah. Okay, great. Okay, so see you next Monday.